Hello, this is the third lecture on software and hardware solutions. The previous two lectures talk about software solutions. In this lecture, we will talk about possible hardware solutions to the critical section problem. This is a very short one. Usually, a modern CPU have has two types of hardware synchronization support. The first one is disabling and enabling interrupts. This is usually slow and difficult to implement on multi-processor system, but we still can do that. We won't be able to discuss how to use it in a very extensive way. But anyway, if you want to learn something, you should be able to learn um, some knowledge in an operating system course. The second one is some special privileged, actually atomic machine instructions. Actually, when we talk about a review of operating system and hardware, we mentioned the compare and swap instruction. But the earliest one is probably the test and set instruction, TS. And there are some other forms such as swap. Now, uh, compare and swapping test and set, if I recall correctly, they appeared in as early as the IBM System 370, which appeared in the early 1970s. So as you can see, hardware support through atomic machine instructions appeared very, very early. It's 50 years ago. So we will review this one and test and set and compare and swap instructions briefly. So the way of using interrupt disabling and enabling is very simple. We have a critical section. The entry sections is usually a instruction, a machine instruction that is able to disable interrupts. Upon exit, use probably a different instruction to re-enable interrupt. Now, disabling interrupt and re-enabling interrupt can only be used in an operating system. That is when the CPU is in the kernel mode. As a result, user programs usually won't be able to do that because user programs run in the user mode. Now, remember interrupts. We learned it a long time ago. Interrupt is just an event that requires the operating system's attention. The hardware will suspend the currently running program and transfer the control back to the operating system. Of course, the operating system must set the CPU mode from user to kernel. Then the operating system analyze what this interrupt is and so on and so forth. Every modern CPU has some instructions that can disable interrupt. That is, after disabling and all interrupts, and then we execute the critical section. Then what if there are interrupt happening here? No problem. Interrupt, just like the signals we learned in our first units, interrupt could be ignored or could be delayed. how this interrupt, how the interrupt that occurred after disabling all interrupt will be handled is probably CPU specific. You probably will learn it in computer architecture or computer organization. But this is unimportant to our course. What you need to remember is after all interrupts are disabled, what would happen? Now, recall the process transition diagram we discussed uh, in the process unit. Process gets to the CPU, either it exits, going into terminated states, or that process executes some instruction in order to wait for a certain event to happen. For an example, input output. So the last important concept is an interrupt occurs, then the executing process on the CPU will be forced off and put back to the ready state. This is the important part. So usually in a critical section, a process would not wait for anything. Usually, not always. And in a critical section, a process will never terminate. Remember, when we talk about the software solutions, we list a few assumptions. Because if a process exits while it is in a critical section, then the exit section will never be able to know the critical section is empty. So basically, what we need to address is once a process is able to disable interrupt and executing in the critical section, then no interrupt could occur. As a result, this process could run from the first instruction after disabling interrupt to the instruction that enables interrupt without any interruption. And CPU or CPU cores will not change hand. In other words, while the process is here, no context switch can occur in a critical section. I hope you remember what I said. Now, if that is the case, the process in a critical section accesses shared variable and no one would compete against with it. No one would compete with it. However, even though this is very simple, an instruction to disable interrupts, another instruction in exit section to re-enable interrupt is so simple to do. But it's usually very infeasible in a multi-processor system because all CPUs and all cores must be informed. Please don't accept interrupts. So how do we do that? In an operating system, usually disable all interrupt. And we need to inform all CPUs and CPU cores that is not only time consuming, but also infeasible to do if you use this technique very frequently. So usually the critical section would be very, very short, just a few instructions. Right after that, all interrupts are allowed to happen. In implementing kernels, you frequently use this technique. And the critical sections is usually very short. But there are some potential problems. For example, some process may depend on interrupts. For example, clock. Whether it's a real-time clock like a sleep or the real-time clock, they may not work properly. For an example, a process, not the process in the critical section, a process executes a slip for 1 second. After 99%, this slip call is done. Then you disable or interrupt in executing something here. Now, because the slip is a real time, clock goes off. So definitely, while you are here, that 1 second could have been expired. So this interrupt will occur after you re-enable all interrupts. Therefore, this timer cannot be very accurate. As a result, when we discuss the system called slip, say for 2 seconds, I always prefer to say you will slip for at least 2 seconds. This is because of the previously stated issue. Your slip is almost done, but all interrupts are disabled. And someone, the operating system, of course, does something in the critical section. It may take several microseconds. Then re-enable or interrupt. At that moment, your timer goes off, or clock goes off, alarm clock goes off, and so on would happen. But that may not happen immediately, because all of the interrupts would be stacked or queued somewhere. When all interrupts are allowed to happen, then they would allow the interrupt to happen one by one. So interrupt disabling, enabling is a technique frequently used in an operating system. And the critical section between disabling and enabling is always very short. Then let's move to one of the oldest atomic instructions that supports mutual exclusion. Test and set. Now, I code the test and set instruction as if it is a function. But because this test set instruction is atomic, all of these statements or operations are being carried out. The pipelines in a CPU would only allow this test and set instruction in execution. All other instructions at various stages of the CPU pipeline will be suspended, and some instruction may be refreshed, operands are reloaded. So what it does, the test and the set instruction requires a pointer to a location. That location, let me call the key. So when you execute a TS, you provide it with a pointer to a location. That location usually contains an integer. Whether it's a byte or 2 byte or 4 byte, that doesn't matter to our course. It's just a pointer to something. So the first step is we copy the contents of that in that location to a local variable called save. And then we stored the value of true to that location and returns the value of the old value. Now, if you read this instruction carefully, you know it's very simple. We get old value and replace the old value in memory by true. and then return the new value. Let me quickly go through it. The TS instruction requires one operand. It takes the operand out and save true to that operand. And finally, return the old value of the operand. How do you return this? The value, usually the value is either true or false. So it may return this true or false value as if it's a condition bit or something, depending on machine architecture and its design. I learned this instruction while I was a programmer waiting for a program running in data center for probably 2 to 3 hours. I was boring. I picked up the principle of operation of the system 370 and scanned through. I found this instruction. I thought this instruction looks quite interesting. Why such an easy thing? Take the value, return it, and replace the old value by true. Why do we need such a somewhat stupid instruction? Until someday, I was able to log into a virtual machine referred to as VM370, starting my study in operating system. Then I know what's going on there. So the TS instruction is an easy tool to implement mutual exclusion. So usually it goes this way. We have a global variable shared by all resources or all processes. Initially, its value is false. So the TS instruction is usually used in the while loop. So reading this one means we provide the value of lock to the TS instruction. The TS instruction replaced the lock by true and returned its old value as the result. Now, if this process is the first one to execute TS, because now the value is false, so TS simply save true to lock and return false. You may interpret in the following way. TS simply returns the value in the location and replace it by true. Now, if that is the case, when TS return true, we simply loop here until TS returns false. If TS returns false, we are here. We will explain it in great detail later. Upon exit, we set the global lock to false and get out. So we simply loop here. Now let's say we have two processes, you and I. So if I am lucky, both of us would want to access this critical section. So if I am lucky, I execute the TS first. Of course, this TS will put true to lock, replacing the old value false. And the TS returns the old value false. Then for me, because the condition in this while is false, so I enter. While I am here, the value of lock is true because this TS instruction did it. Now, if I am here, you try to enter by going through this entry section. So what you execute is you get old value of lock, which is true. And then the TS instruction put true back to the lock and returns the old true. Now, this kind of interesting. Now, let me rephrase it in this way. When you execute a TS, because last time when I execute TS, true is put into lock and the TS returns false, right? So I am here. Once I am here, what if you try to execute TS again? Recall that lock has the value true here. I set it through the TS instruction. Then when you execute TS, TS replace the old true value by a new true value. And the old true value is returned as a result of the TS execution. So this while we see that, okay, the return value is true, so we do it again. The next time you execute TS, you put the third true value into the lock variable, and the second copy of true value is returned by TS. So you keep doing this over and over until I exit and save false to lock. So once the lock receives the value false, the next time you execute the TS, then you put true into false. And the TS returns you the old value, which is false, reset by me. Therefore, you can enter. Hope you understand this. Okay? Now, you may ask the question, what if you and I execute the TS at the same time? Worrying not, because TS is an atomic instruction, which means if multiple atomic instructions are issued to a CPU, the hardware will execute this atomic instruction sequentially. So if you and I execute the TS instruction at the same time, the hardware will determine whether you go first or I go first. So if the hardware determines that I should go first, so I get here and enter. And once I am here, when you execute your TS, you are blocked. Now, if the hardware determines that you go first, so when you execute the TS instruction returns the old value false and replace the old value false by true, and you enter. After you enter, the hardware allow me to execute the TS. Always remember, TS is atomic. So when I execute TS, the TS instruction puts the second true value into lock and return the value you saved to lock to me. So I am looping. In this way, mutual exclusion is sort of established. It's even more important. So far, what we have learned in the software solution part, we are only able to do with two processes. Now, if we have many processes that may want to access this critical section, every process just execute TS with respect to the same lock. Upon exit, simply set the lock back to false. We are done. If these processes execute their TS instruction in a sequential way, fine. The first one doing the TS would enter. Now, if these processes execute TS at the same time, because TS is atomic, only one could get through. Once that one gets through, all the remaining would be blocked. because the lock value becomes true until the one in the critical section exit and that sets lock back to false. So this is a way to implement mutual exclusion. We haven't proved it yet. We just provide you some discussion. We haven't proved it in a rigorous way. Now, we talk about a good solution to the mutual exclusion problem. What are these three conditions? Mutual exclusion seems to be true for this solution. How about progress and the bounded weighting? Sorry, we have no way to guarantee bounded weighting would be satisfied because process running in different speed. Some fast running, let me call it fast runners, could frequently come back, block other processes from entering. Progress, now think about it. Progress in this implementation should be true. Outsider have no way to influence the decision making by the TS instruction. And the decision making is definitely finite. Suppose we have two processes waiting here, executing TS. The hardware pick one. Look here. Previously, the decision making is implemented in the entry section. In the software solution, we use BC loops. But now, if the critical section is empty, the value of lock is false. No matter how many processes are executing the TS command instruction at the same time, only one would succeed because the hardware would execute this atomic instruction one at a time. So mutual exclusion appears to be true. Progress is holds, but bounded weighting is a problem. So let me quickly go through it. A process can enter its critical section if the TS instruction returns false. Now, before we actually prove this algorithm satisfies mutual exclusion, please pause and make sure you understand what I explained. Always remember the TS instruction is atomic. Please pause. Now, let's prove rigorously based on what we have learned so far. This is the algorithm, entry section, exit section. Now, let's study P0. We only use two processes. You can easily extend this to arbitrary number of processes. So P0 can enter its critical section if and only if TS returns false, right? And because this algorithm is completely symmetric, you can easily say that P1 is in its critical section if TS returns false to P1 here. Now we have found the condition for P0 to enter and the condition for P1 to enter. For P0 to enter, if TS returns false to P0. If P1 is in the critical section, if TS returns false to P1. Now, what if P0 and P1 are in their critical section at the same time? So P0 and P1 both receive false from TS instruction. Can that happen? Can that happen? I would say no. Because P0 and P1 cannot execute TS instruction at the same time because TS is atomic. Therefore, P0 and P1 can only execute their TS instruction in a sequential way. The one who executes the TS instruction gets false. While that one is in the critical section, the other one would always get true value returned to CS. Therefore, we have a contradiction. In other words, P0 and P1 cannot get false return from the TS instruction at the same time. As a result, mutual exclusion is established for P0, P1. And you can repeat it many times. P0, P1, P2, P3 to Pn are all in critical section. But P0, P1, P2, P4 to Pn, they must execute the TS instruction in a sequential way. Only one can execute TS at any time. Therefore, only one can enter. So that means these processes would not be able to get false return at the same time. So as you can see, TS as an atomic instruction, it guarantees mutual exclusion very, very easily. So before we continue, please make sure you understand how mutual exclusion implemented by TS in this way holds completely. Please pause. Then let's talk about compare and swap again. So to compare and swap, I use CS. Some literature may use CAS, where A could be uppercase or lowercase. So the compare and swap instruction takes 3 operands. The first operand is a pointer to a location, just like a test and a set. The next 2 are 2 values. And they could also be pointer to locations, okay? So the compare and swap goes as follows. Compare the O value against the value stored in P. If they are not equal, we return false. If they are equal, we replace the value here by the new value and returns true. Very similar to a test and set. So let me quickly go through it. New and old and new are 2 values. P is a pointer to a location, just the lock we mentioned. So CS compare the value at P against the O value. If they are not equal, we return false. If they are equal, we replace the value at P by the new value and return true. Again, CS is atomic. If multiple CPUs executed are issued with a atomic instruction, always remember, just like a test and set, the hardware will determine who would go first, so that all of this atomic instruction will be executed in a sequential way. So here's an implementation of mutual exclusion. Remember, just like a lock, initially we have false. Now, we send the lock and the false and true to the CS instruction. What the CS instruction does is compare the value stored here against the second operand, the O value. If these 2 are not equal, it returns false. And if these two are equal, then true will replace the value of lock here and return true. So that means we have lock value here. If the lock value is the same as the old one, return false. Then I will try next time. If the old value is equal, if the old value is equal to the current value in lock is equal, then I put true to there. Isn't it very similar to test and set? So now let's take a look at this. The current value is false. So I executed CS. So we compared the value in lock and the old value. Because they are the same, then true will be saved to lock and returns true by the CS. Now, not true means, well, the condition fails, we get into the critical section. Now, while I am in the critical section, the value in lock becomes true because the new value replaces the old value. Now, what if you execute CS while I am here? What you see is the lock value is true. Now you execute CS in the same way. So we use the old value, false, and compare against the lock value. They are not equal. Therefore, CS return false, and not false is true. Therefore, you loop here until I set lock to false. Isn't the concept is essentially the same as test and set? But why we need a different instruction? Because CS has more things to support. So it's likely that this implementation for mutual exclusion is true, just like what we saw for TS. Now, how about progress? Of course, you can simply duplicate what we set for TS. Now, how about bounded waiting? Well, it may not be true exercise. Now, please stop here and understand. Just use two processes, A and B, to make sure that you understand this implementation does block the other guy if someone is in the critical section. More importantly, what if two processes execute CS? Because CS is atomic. Therefore, only one of these two would execute. That is, the hardware would force these two processes to execute CS in a sequential way. So please stop and understand the mutual exclusion part. And please also follow the TS proof to show this implementation does satisfy mutual exclusion as an exercise. Please, first of all, understand how mutual exclusion is implemented. I copied the CS instructions here. As we saw earlier, CS is useful for building mutual exclusion. Now, because CS is atomic, it offers a fast way for updating variables, such as doing count plus plus and count minus minus in a mutually exclusive way. Here is an example we discussed a few weeks ago. We have a shared variable count. This shows you one process. So initially done is set to false. As long as it's not done, we retrieve the value of count to a local variable VAL. And then we want to update the count value by adding 1 to it. And then we use the CS instruction to do it. The CS instruction compare whether the saved local value is the same as the global value. If they are the same, we use this new value, adding 1, to replace count value. If they are, and returns true. And if the values are the same, returns not the same, we return false. Now, I hope you still remember this example. So, why must we save the value here? It's obvious. If you don't save it, and what if after doing while, you may have a context switch? Before you can execute this and use directly the count value here and here, somebody could have updated, even though that somebody may execute the CS at the same time as you do. The hardware will choose a process to execute that atomic instruction. Now, if that is the case, that process may have updated the value of count to something. Say, if the origin is 0 and you want to make it 1, but that process made it 1. So are you going to add 1 to that 1, or are you going to add 1 to the original value 0? Of course, your intention is adding 1 to the original value 0. But the other process runs faster and making progress earlier than you do. So that process updates the value of count to 1. Then you should not add 1 to that. In this way, if that process can do it faster than you can, so what you do is copy that process's value to a local variable and use this local variable and your local variable plus 1 for using CS. That is only if the variable is 1 less than the value I want to achieve. Then I do an update. Hopefully you understand this example. Of course, you can do that. One process can add 1 to it, the other process could subtract 1. And this is very commonly seen in implementing the kernel. For an example, when we talk about locks and the semaphores, we usually need to count how many people are waiting there. So we need to add 1, add 1. When we release a waiting process, we need to subtract 1, subtract 1. So how do we do this? Simply put, this is it, or subtract, by the use of compare and swap. I hope you understand this example. And finally, let's discuss some problems. First of all of these solutions use busy waiting. Busy waiting means a process waits by executing tight loop to check the status or value of a variable. Busy waiting may be needed on a multiprocessor system. However, it simply wastes CPU cycle that some other processes may use productively. But once you get into an operating system course and implementing locks and other mechanism for your user to use, so that they don't have to use disabling, enabling interrupt, and they don't need to use atomic instruction. Of course, you don't need to use a software solution because that's very time consuming. Then you need something inside the kernel to do that. So busy waiting is nearly unavoidable in a kernel. But anyway, when you do busy waiting, make sure that the critical section has to be very, very short and very small so that you get in and get out very quickly. Now, some systems may allow user to use some atomic instructions such as Intel x86, unless the system is lightly loaded. If you use atomic instructions so frequently, CPU and system performance can be low. Although, from a programmer's point of view, he or she may think and his program or her program looks more efficient. But indeed, from the hardware point of view, if you use this atomic so frequently, multiprocessors and multi-cores must serialize these atomic instructions. Therefore, we need better solutions. Usually, these better solutions are supported at the kernel level through system calls or something else. In this course, we will talk about semaphores, monitors, and lock, and so on. But that is in the future, not now. And this is the end of this very short discussion of hardware support. I hope you are able to understand test and set and compare and swap, disabling and enabling interrupt. These mechanisms are usually used in an operating system to support mutual exclusion for the users, or even serialize something that could happen in the operating system. So let me stop here. See you next time, and goodbye.